So we're all in on AI, right? We're using it for these huge, sometimes life and death decisions in healthcare and finance, you name it. But there's this one nagging problem, this big black box issue. A lot of the time, we have no idea why the AI is making the decisions it's making. Now, we've got tools that are supposed to help us peek inside that box. But what happens when those tools look at the exact same problem and give us completely different answers? Who do you trust then? Okay, let's make this real. Imagine you're a doctor. You've got an AI that's flagging a tumor as cancerous. So far, so good. But you need to know why. So you run two of the best AI explanation tools out there on the exact same patient data. And tool number one says it's because of feature A. But tool number two says, no way, it's all about feature Z. So what do? How is that even possible? Which one do you bet your patient's life on? That is the puzzle we're going to dig into today. All right, to get our heads around this, we got to talk about two totally different ways of seeing the world, or in this case, seeing our data. You've got the local view and the global view. Think of it like this. The local view is like walking up to a single specific tree in a massive forest. You can study its bark, count its leaves, you know everything about that one tree. But the global view, that's like climbing the tallest mountain around and looking down at the entire forest. You see the patterns, where the pines grow, where the oaks are, the whole landscape. Two very different perspectives, right? So the tools we've been using for years, and you've probably heard of them, things like SHAP and LIME, they're absolute masters of that local single tree view. They're amazing at saying, hey, for this one patient, the tumor size was the deciding factor. Super useful. But, and this is a big but, they have a massive blind spot. Because they're so focused on that one tree, they're completely oblivious to the forest. They have no idea what kinds of patterns or patient groups exist across the entire dataset. And that's where our story takes a turn. See, a new tool called ARCHEX just entered the scene. And it's built from the ground up to fix this exact problem. It's not interested in individual trees. Nope. Its entire mission is to give us that bird's eye view, to finally map out the whole forest. Okay, so how does it do this? Well, under the hood, ARCHEX is using something called archetypal analysis. And it's a really cool idea. Instead of looking for the average patient, which, let's be honest, might not even exist, it hunts for the extremes. It's trying to find the purest, most textbook examples in the data. So think about finding the patient with the absolute most complex tumor, or the one with the smoothest tumor, or the one with the largest. These extreme profiles, those are our archetypes. And the process itself is actually super straightforward. Step 1, ARCHEX digs through all the data and finds those extreme cases we just talked about. Step 2, it tags them, saying, okay, you're an archetype. And then for step 3, and this is the magic part, it describes every other patient as just a simple mix of those core archetypes. So what you get at the end is totally different from a boring list of numbers. A doctor might see something like this. And yeah, this is a real quote from the research. It's so much more intuitive, right? It tells a story. It places this one patient within the context of everyone else. It's not just a data point, it's a profile, a whole new way of explaining things. All right, that's the theory, but does it actually work in practice? Well, the researchers put it to the test. They took a famous dataset, the Breast Cancer Wisconsin dataset, and ran ARCHEX right alongside SHAP to see what would happen. And what they found was, well, let's just say it was pretty shocking. And boom, here it is. This chart tells the whole story. Blue is ARCHEX, orange is SHAP. Remember, they are looking at the exact same data for the exact same model, and yet it's like they're from different planets. ARCHEX is basically shouting from the rooftops that mean fractal dimension is the #1 most important feature. Meanwhile, SHAP is way down the list, focusing on completely different things. It's a total disagreement. Let's put some hard numbers on that. Look at this. The thing ARCHEX says is #1, SHAP ranks it way down at number 19. That's a gap of 18 spots. And it gets crazier. Fractal dimension error is #4 for ARCHEX, but SHAP has it at 29th. That's a 25 rank gap. We're not talking about a minor difference of opinion here. This is a fundamental clash. Yeah, just let that sink in for a second. Plus 25. A feature that one tool says is critical to understanding the big picture is basically invisible to the other. This is the perfect example of that forest for the trees problem. If you only used SHAP, you might never realize how important this pattern is. So what's going on here? Well, SHAP isn't wrong. It's doing its job perfectly, picking out the little details that nudge one specific prediction one way or the other. But ARCHEX is playing a different game entirely. It's seeing these massive global patterns. It's identifying two fundamentally different types of patients in the data, those with smooth tumors and those with fractal or complex tumors. That's a huge clinical insight that the local view just completely misses. Now, your first reaction might be, okay, so which one's right and which one's wrong? But here's where the researchers drop a bombshell. They argue that the disagreement, that's not a bug. In fact, it's the most important feature. The fact that they disagree is the biggest clue we have. This chart proves it. See, if the bars were high, it would mean the two tools basically agree. But look at that bar for the breast cancer data. It's tiny. It's almost nothing. What that tells us statistically is that these tools aren't telling us the same thing twice. They are giving us genuinely unique, non-overlapping information. The actual correlation number is, get this, 0.075. For anyone who knows stats, that's nothing. It's basically zero. It means the insights you get from SHAP and the insights you get from ARCHETYPES are coming from completely different angles. They're not just different, they're perpendicular. Which brings us to what is, for me, the killer line from this whole paper. The low correlation we observe is not a bug, it's a feature. I mean, that's it right there. That's the mic drop. It means ARCHEX isn't a replacement for SHAP. It's a completely new lens, a new dimension for understanding our models that we just didn't have before.
So let's just boil it down. They're answering two different questions. SHAP answers, why did the AI make this one prediction for this one person? That's the local question. ARCHEX answers, what kind of fundamental patient groups even exist in my dataset? That's the global question. You need both answers to really know what's going on.
And hey, for all the tech folks out there, you might be thinking, this sounds slow. Well, they thought of that. They build it to run on GPUs, so it gets a massive 10 to 100x speed boost. That makes it totally practical to use this stuff in the real world, in real time. So what's the takeaway for anyone actually building or using these systems? It's a new workflow. Step 1, start with ARCHEX to get the lay of the land, to see the whole forest. Step 2, then use a tool like SHAP to zoom in on individual trees, the specific cases you care about. And step 3, the most important one, when they disagree, that's not a problem. That's a discovery. That's a big flashy neon sign that says, hey, dig here, there's something new and interesting to be found. And that really leaves us with a big question to think about. For so long, the hunt and explainable AI has been for that one perfect tool, the one ring to rule them all. But maybe that's just the wrong way to think about it. What if the future isn't about finding a single tool, but about building a better toolbox, and knowing that true understanding only comes when you combine different views, when you can see both the tree and the forest?